Hello guys, welcome back to my channel Gamma Digamma. So in this video, I sort of wanted to continue our discussion of the applications of residue theorem in calculating real integrals. So I believe we discussed like choosing contours in the last video. In this video, let's talk about something a little more interesting. Let's get started. First part of the video, we will be discussing definite integrals of trigonometric functions. So it's usually going to be 0 to 2 pi d theta w sine theta cosine theta. So this is a function of sine and cosine. What you do in such cases, you take z equals e to the I theta, so that you have, I'm skipping some steps, d theta as dz over iz, and then sine theta by Euler's formula 1 over 2i e raised to I theta minus e raised to negative I theta, which just becomes z minus 1 over z, and then cosine theta is 1/2 e to the I theta plus e to the negative I theta, which becomes 1/2 z plus 1/2. So it's simple, just substitute e raised to I theta with z, you get these things. Okay, what this means is like the structure we had for our original integral, the integral from 0 to 2 pi d theta w, a function of sine and cosines, now just became integral dz over iz w of z minus 1 over z over 2i comma z plus 1 over z over 2. This is just a regular 2. And let's look at the upper and lower bound. So the lower bound is 0, so you plug in 0 in place of theta and then you see what value of z you get. Well, you get e raised to 0, which is 1. Fine. If you plug in 2 pi, e raised to 2 pi is also 1. So is this like 0, integral from 1 to 1, that is 0? Well, no, actually not, because since when we introduced e raised to I theta, we're actually working on the complex plane, and in the complex plane, e raised to I theta is indeed 1, but it's not the same as e raised to 0, e raised to I times 0, because when you say 2 pi, it means it's completed one revolution in an anti-clockwise direction by convention. So this becomes a closed contour integral, and since we have this substitution, the magnitude of z is 1. This is going to be a unit circle centered at the origin, so on the complex plane. That's how you denote it. So whenever you have 2 pi and you use this kind of substitution, you're usually going to end up with this. That's why, look forward to convert an integral, even if it's like not in a 2 pi form. Try to use symmetry, try to convert it in 2 pi, because that's when we can actually use some residue calculus, because notice we have a contour, we have some region enclosed by the contour, and then there will be singularities in there, and then we can use the residue theorem inside that region. We need an enclosed region for the residue theorem to work. So I'm going to give you a good example of this. This was, I think, lots of theory. One good example and maybe another one should drive home the point. Okay, say we have I as integral from 0 to 2 pi d theta over 2 plus cosine theta. So, I mean, I'm just skipping steps. We can use the substitution here on top to get closed contour integral for a circle, unit circle centered at 0. F dz over iz 2 plus, in place of cosine we'll have z plus 1 over z over 2. So just kind of like simplify the denominator. Negative 2i contour integral dz over z squared plus 4z plus 1. Well, so since we have like a contour integral, we can try using residue theorem. So we have to check what poles are inside the contour. So for poles, we need to basically check whether the denominator is going to be 0 at any z. So z squared plus 4z plus 1 is equal to 0. Try using the quadratic formula. And we have 16 minus 4. I'm skipping lots of steps. I hope you know this. This is going to be negative 4 plus or minus 2 root 3 divided by 2, which is negative 2 plus or minus root 3. So we have like two possibilities. It's either negative 2 negative root 3, or it's negative 2 plus root 3. Well, we can just check which ones are inside. Root 3 is approximately 1.732. So negative 2 minus root 3 will be something like negative 3.732. So you notice like the magnitude of this guy is greater than 1. So it's going to be like outside the contour somewhere. On the other hand, z0, which I will now call negative 2 plus square root of 3, the magnitude of that is like less than 1. So it's going to be inside the contour, and that's what we're going to care about, right? Because we only care about points inside. So for that, well, it's a simple pole because it was a quadratic. You can factor it out as z minus z0 and z minus like this guy. So for a simple pole, it's pretty simple. Limit as z goes to negative 2 plus square root of 3, z plus 2 minus square root 3 times 1 over 4z plus z squared plus 1. So we can like factorize out the denominator. Z plus 2 minus square root of 3. Denominator, using these factors that we found out, can be factorized as such. So these guys conveniently cancel out, and we're left with 1 over 2 root 3. Well, that's still like the residue, right? This is the residue. We had I as negative 2i and then the contour integral, but the contour integral is just 2 pi I times the residue enclosed. So 2 pi I times the residue enclosed, which is 1 over 2 root 3. So the I and the negative I will cancel off to 1. One of the 2's goes away, and we finally end up with 2 pi over square root of 3. So you notice how nice this method is. Like this looks pretty innocent. Like there's no real motivation for like a complex analysis kind of approach. It's not even an improper integral. It's a proper integral over a periodic interval. I mean, this example was pretty simple. You can do this by a Weierstrass substitution. But like if you have like a square or something like that, or a cube or a higher powers, it's going to be harder and harder to solve this. So that's when complex analysis kind of reduces the problem to just solving or finding the pole, then the residue, and then plugging that into the formula. Let's do another example which is a little more useful. Okay, so question at hand is integral from 0 to pi d theta over 1 plus sine squared theta. Notice this is not in our standard form. Upper limit is not 2 pi, it's pi. So let's try to exploit symmetry. Well, notice that sine theta is equal to sine of theta plus pi. This is a well-known property of the sine. You may want to revise your pre-calc or your advanced trigonometry for this. But with this, you can have same thing. 1 plus sine squared theta plus pi. Now let's use like a substitution. Theta prime is theta plus pi, so d theta prime is d theta. Upper and lower bounds, however, become pi and 2 pi. And we have 1 plus sine squared theta prime. And since it doesn't matter really what variable we have for a definite integration, we can just change from a theta prime to a theta again. And now this integral, add that with this equation. So we have I plus I, which is 2i, and then you have integral from 0 to pi d theta over 1 plus sine squared theta plus integral from pi to 2 pi d theta over 1 plus sine squared theta. By linearity of integration, definite integrals at least, this becomes integral from 0 to 2 pi d theta over 1 plus sine squared theta. So I is just half of that. So this is how we use symmetry to see that so to convert basically an integral, an upper bound to an ideal upper bound, so that we actually get a contour integral. If you use your exponential substitution for the pi case, you're gonna get integral from 1 to -1, like along a like a semicircle, which is not really that convenient to solve. It's kind of painful. Okay, so let's try to solve this. We can use our substitution now. So z becomes e raised to I theta. So I is just 1/2 dz over iz. 1 plus, in place of sine, I have z minus 1 over z over 2i, the whole thing squared. Then put like a square bracket on it. So this is just a matter of like some simple algebra here. 1 over I is negative I in the numerator. You have dz over z times 1 minus 1 over 4z squared, z to the 4th minus 2z squared plus 1. And then we have, 4z squared, sort of common denominator that thing up. 4z squared over z multiplied by 4z squared minus z to the 4th plus 2z squared minus 1. So we can like suck this negative, like change like the order of the denominator with that, because we want the higher order power term, the 4th power, to have a positive coefficient. 2z dz over z to the 4th minus 6z squared plus 1. This is still a quadratic, but you'll be in place of solving for like z, we'll be solving for a z squared, because now we need to find the poles, right? And then the residues. So z squared is plus 6 using the quadratic formula over 2, which conveniently becomes 3 plus or minus 2 square root of 2. So z has like actually 4 possible solutions. So z plus plus is 3 plus 2 square root of 2. Z plus minus is 3 minus 2 square root of 2. We have a z minus plus, which is going to be negative 3 plus 2 square root of 2, and a z minus minus, which is going to be negative square root 3 minus 2 root 2. So it's kind of obvious. I hope it is to you. But these guys, these z plus plus and z plus minus, sorry, z plus plus and z minus minus, they have like a magnitude that's like slightly greater than 1. So we can't, they're not enclosed inside the contour. So we have to like drop them. We don't really care about them. Let's just talk about these two guys. Well, both of them are going to be inside the contour on either side of the of the imaginary axis. They're basically going to be on the real axis, but like reflected across the imaginary axis. So let's do this for, let's say, z plus minus. It's a simple pole. So limit z goes to z plus minus, and we have z minus square root of 3 minus 2 root 2 multiplied by z, because z was like in the original. I'm not taking the 2i right now. We had a z on top, so that z is a z squared here and a z there, divided by, like, the denominator was like unchanged. So we can now use L'Hopital's rule because we have a 0 over 0 condition. So limit as z goes to z plus minus 2z minus square root of 3 minus 2 root 2 divided by, I have a 4z cubed minus 12z. In the numerator now we can actually like plug in. So 2 times this guy minus that same guy is 1 times that guy, divided by, we can plug out like a 4z out and then take the limit. So 4 times like z plus minus, which is this guy, 4 times square root 3 minus 2 root 2, and then since we took a 4z out common, we're left with a z squared minus 3. Z squared is basically this thing squared, so 3 minus 2 root 2 minus 3. So you notice like nice things going on here. This cancels out, the 3 cancels out, and we're just left with negative 1 over 8 root 2. That's the first residue. We still have one more residue to go. Residue 2, limit as z goes to, let's see, minus plus. So with that, we just have like a similar process going on, except we now have a plus sign. So we have a z squared plus square root of 3 minus 2 root 2 multiplied by z divided by z to the 4th minus 6z squared plus 1. Again, L'Hopital everything up. Limit as z goes to z minus plus 2z plus square root of 3 minus 2 root 2 divided by 4z cubed minus 12z. So we have 2 times negative of something, because z minus plus is like negative, plus that thing, we just get a negative 1 of that, divided by, again, like take 4z out common and then take the limit. So we have 4 times the same thing, z minus plus basically, and then z squared minus 3 like last time is basically the same, because the square of a negative is still, and a positive will be the same. 3 minus 2 root 2 minus 3. 3's cancel out, this negative cancels out, and this factor cancels out. So we are again left with negative 1 over 8 root 2. That's residue number 2. So the sum of residues now, because these are the only residues enclosed, is this plus this. So this twice basically. Negative 1 over 4 root 2. We know the sum of residues. Now we can actually use the residue theorem, because we can just substitute that for this contour integral. Remember, we hadn't taken a 2i into consideration. Let's do that now, because now we have 2i times the contour integral, which by residue theorem is 2 pi I, times the sum of residues, and the sum of residues we calculated above to be negative 1 over 4 root 2. So the I squared will be a negative 1, that cancels out with this negative. 2 times 2 goes with the 4, and we are just left with pi over square root of 2. You know, I just like the fact that there's like so many pies in these integrals. They just like pop out because of like this residue theorem, 2 pi I factor. It's just so nice. So I hope this convinces you, and with this we come to the conclusion of our discussion of the definite trigonometric integrals. Okay, now what we're going to talk about is something that is not really like talked about much, basically at a really basic level, but which albeit merits our attention, at least for this half of the video. I'm going to talk about principal parts. Before starting on this discussion, I would like to consider integral from negative infinity to infinity dx over x cubed. Well, what is this? Is it 0? Well, look at it. It's an odd function over a symmetric interval. It should go to 0, right? I mean, I can sketch it out for you if you want. Our intuition tells us clearly it should go to 0. If you interpret integrals as like areas under curves, if I sort of like graph this up, it's basically the area that I'm going to shade here. So we have some negative area on the negative side of the x-axis, and then some equal magnitude positive area on this side of the axis. So I mean, both areas should cancel out, right? Signed areas integration. It's one way of thinking about this is like, think of like sort of cancelling infinities. Why do I say infinities? Because there's like this 0, x equals 0 point that like lies at the center, and at that point the function diverges, like the limit doesn't exist. It just blows up. Like take approach from the left side, it goes to negative infinity. Approach from the right, it goes to positive infinity. A big jump discontinuity, and on top of that, a divergence. So when we're integrating this, and if our intuition tells us it's going to be 0, and if you look at the geometry of this, it will. Which means that like these divergences cancel out. Like these infinity minus infinity is like 0. That's essentially what it's like hinting at. So what's really going on? Well, to consider integrals such as these, we consider what's called a principal part. So which like sort of like the part. This is somewhat like regularization. It's like sort of like taking a part of this integral that actually like intuitively makes sense. It's kind of like that. It's like surgically removing that troublesome area, if you want to think about it that way. So what you do is to take the limit as epsilon goes to 0. Then you have integral from negative infinity to negative epsilon dx over x cubed plus integral from epsilon to infinity dx over x cubed. So just take like a few minutes to realize what I've done. You see this 0, I've sort of created like this arbitrarily small sort of like pocket around it, like a trench around it, like 0's in the middle. This is negative epsilon, this is positive epsilon, and this is arbitrarily small, and I'm taking the limit at that epsilon goes to 0 because we still want to like sort of make sense of this original guy, right? We still want to stick to the original integral that we had. But doing this, since this is not really 0, it's like really small, arbitrarily small, like we say in real analysis, we can actually find the antiderivative of this because it doesn't diverge. This will be negative 1 over 2x squared negative infinity negative e epsilon plus negative 1 over 2x squared. We have epsilon and infinity, and even without taking the limit, you can see that these like epsilon terms cancel out, and the infinities basically will make the entire thing go to 0. So you're just left with negative 1 over 2 epsilon squared plus 1 over 2 epsilon squared, which becomes 0, and this goes faster than this limit. Both of them cancel out each other even before the limit can make them go to 0. So this actually like goes faster than the limit, and that's why it sort of makes sense to talk about principal parts. We aren't really doing infinity minus infinity. It's like the infinities are like of the same side, so this thing is like justified in this case. Otherwise we don't know the relative magnitude of the divergences. In this case they're the same, that's why they sort of cancelled each other out, mutually annihilated each other out even before the limit could. So in general, if some function blows at x equals a, because in the previous case our function blew up at x equals 0, then what do you do? If you want to take the principal parts, you're integrating from negative infinity to infinity. What you do is just like chop up the interval, and you need to like mention principal parts, otherwise I would say it's a mathematically healthy habit of doing it. Negative infinity to a minus epsilon, so that singularity point minus that epsilon, dx w of x, and then for the other part a plus epsilon and infinity, you guessed it. So this is what you do, and then like before, find the antiderivative if it exists, or what, do your calculations and notice that those epsilon parts sort of mutually annihilate each other out, irrespective of the limit, faster than the limit actually. So if you want to think of this in like terms of definite integrals in like of single variables, sort of like this, you're integrating along this line from negative infinity to infinity. You have a, you create like this trench around a, so you have a minus epsilon, and you have a plus epsilon, and epsilon is arbitrarily small. So that's basically what you're doing. Now we would like to extend this method to contours, and then our principal parts will be now called Cauchy principal part. So let's sort of extend it to contours, complex analysis basically. So principal parts of a real integral, because you can convert like a real improper integral like this into a contour integral. I didn't need the second integral. I'm sorry, it was just a slip of hand. dz w of z, which basically means like I've complexified it, and this is only possible once you like have contour integral around some c, dz w of z is equal to sort of like the part on like the real axis, but the part on the real axis alluding to before is going to be the regular principal parts, you know, from the single variable case of dz w of z, and the z will become an x eventually, then some top part, and then one part that I will sort of discuss, this gamma part. So I'm going to draw a picture of what contour C looks like, assuming, and it will always be the case, at least when you're doing Cauchy principal parts, that sort of the point of blowing up will occur on the real axis, just like in the single variable case. So that's why I have a PP written for this first integral component. So assume that's at like a here. What you do is, since you're in the complex plane, you are allowed to loop over. We're not in the single dimensional case. We can loop over things and continue, because having this singularity on the boundary, it's like really bad, topologically speaking. And then sort of close it up in a anti-clockwise direction. Again, since it's negative infinity, positive infinity for the original guy, we have negative r, and we'll take the limit as they go to infinity eventually. So this arc is like the top part that will go to 0, you guessed it. This is a minus epsilon, this point is a plus epsilon. This sort of curve, we'll have to account for that. We'll have to like do a special contour sort of integration expression for that, call that gamma, and that's why I have this gamma term here. So we have to account for the exclusion or inclusion. In this case we're including it because it's inside the contour, the entire collective thing. We can jump over it and exclude it, but you see, for a meaningful Cauchy principal parts integral evaluation, both inclusion and exclusion should give you the same answer, as we will see in the couple of examples that I will do. So this gamma is to account for the inclusion or exclusion. Exclusion is important because that affects how we're going to calculate our residues. If we jump over it, we won't need to calculate that as a residue. If we jump under it, that will naturally become a residue inside, or pole inside the contour, which will have to be sort of used as a residue. So consider the following principal parts of negative infinity to positive infinity dx over x squared plus 1 x minus 1. This can be expressed as principal parts of like the complex version of this, which means that we'll have to subtract from the contour integral those other integral terms, which includes the top arc part and this new gamma part that I just showed you a couple of minutes ago. A contour isn't that different. We're choosing to include it. I will also exclude it for the next case. So this is negative r, this is r. Loop over upper cap. This is 1 minus epsilon. This is 1 plus epsilon. If you notice, the pole is at 1 because of z minus 1 factor. And this is gamma. Well, for the upper cap part, we have limit as r goes to infinity. Integral from 0 to pi because it's a semicircle. Magnitude of epsilon I e to the I theta d theta. I'm just skipping steps of the estimation lemma here. But it's kind of easy to see, even at this stage, that the only r factor comes from the denominator, an accumulated power of 3. So it inevitably will go to 0 in the limit that r goes to infinity. So I won't really spend too much time on this. And now for this gamma part, since it's a semicircle centered at z equals 1, I'm going to have to parameterize that as z equals 1 plus epsilon e to the I theta, because the radius is epsilon everywhere. Our integral will go from, like, since it's like in the lower half of the circle, it's going to be from pi to pi. You can plug in things. So pi will give you a negative. So you get this point. And since we're going in the direction, it obeys the direction pi to 2 pi, and 2 pi will give us 1, which is what we have. So it clearly makes sense. Let's see. Limit as epsilon goes to 0, because we need that. That's like our principal part sort of condition to make sense of all this. Epsilon I e to the I theta d theta divided by 1 plus epsilon e to the I theta whole thing squared plus 1 epsilon e to the I theta. This just becomes limit as epsilon goes to 0 I times pi 2 pi d theta over 1 plus epsilon e to the I theta squared plus 1. You notice that epsilon goes to 0, we just have like a 0 here. 1 plus 0 is 1, and we have a 2. So this becomes I times 2 pi minus pi, which is pi over 2. That's the gamma integral. For the contour integral, just use the residue theorem again. Notice we have two poles in there. We have z equals I as the pole, because this factors out into z plus I, z minus I, z minus I, or z is equal to I is inside, z equal to minus I is outside. So we have z equal I and also this 1 because we chose to include it. So that is going to be contour integral dz z squared plus 1 times z minus 1 is now going to be 2 pi I times the sum of residues. I've skipped some steps. Calculations are easy, they're simple poles, you can do it. 2i, I minus 1 plus 1/2. And we have pi over I minus 1 plus I pi. Sort of multiply and divide by the complex conjugate. We have a 2 here plus I pi, which becomes I minus 1 pi over 2. Fair enough? Which means the principal parts of the thing we wanted to find is now just I minus 1 pi over 2, like the contour part, minus the gamma integral, the epsilon part. And this results in negative pi over 2. And this is a satisfying result because we don't have any imaginary i's. We don't have any imaginary parts to this. And it should sort of make sense because this is a real integral. A principal part of a real integral, yet still. And now, just for the sake of this argument and to conclude our discussion, let me sort of try excluding that pole at 1 that was on the axis, real axis, where we drew our line of integration. So like the contour otherwise will like remain the same. Gamma is like the top guy now, and the cap part, we have r and negative r here. There's nothing strange about that. And as always, limit as r goes to infinity of the top guy, dz over z squared plus 1, z minus 1 will go to 0 because the r's will accumulate in the denominator, making it go to 0 in the limit. For the gamma part, however, again just follow protocol. Now we go from pi to 0 because we are going in a clockwise direction. That's why the order of integration is reversed. Divided by epsilon e to the I theta plus 1 squared plus 1 epsilon e to the I theta. So stuff cancels off like it always does, and you're just left with like an I, and then even this guy will become 0 in the denominator, so you just have negative pi after doing this integral with a factor of 2, so you have negative I pi over 2 like before, except no, before we just had a positive, now we have a negative. So well, nothing really special about it. You plug that into the formula because this guy is just going to be the contour integral minus these individual contributions. So the contribution from the top arc was 0, so just forget that, minus the contribution from gamma, so minus of this is going to be plus I times pi over 2. Again, sort of do the residue theorem, but now notice that the only pole that's inside the contour is at z equals I because we chose to exclude z equals 1. We had to do that calculation before, so it's kind of at times convenient to like just ignore or just exclude that which lies on the axis. So 2 pi I over 2i I minus 1 I pi over 2. I'm just skipping lots of steps. You can pause the video, do it on a piece of paper, because if you've watched my videos you know how to calculate simple poles, residues, and you again get negative pi over 2. So it shouldn't be much of a surprise because principal value sort of satisfies our intuition. It says that it won't really like diverge that bad. You can assign a value to that divergence, sort of like regularization. I mean, regularization takes birth because of stuff like this, like surgically removing or taking care of those singularity points. And again, it wouldn't make sense if, you know, we got two different answers for excluding and including that point. So this means that, you know, this is actually a valid approach. There's like an entire theory behind this. Principal parts. This was Cauchy principal parts for complex integrals. So yep, I hope you like this video. I think that's it. That concludes our basic complex analysis video series. Please like and subscribe to my channel, guys. Recommend me to your friends. Spread the word of gamma diagram in the math community. I have no real clear idea what I'm gonna do for the next videos, but stay tuned nevertheless, because I don't disappoint. I might, even go into some advanced complex analysis, and then that will basically like tip off into like analytic continuation and like Schwartz reflection principle and stuff like that. So let's see how far we can go. Peace out till then. Stay tuned.